All right, good morning, everyone. So in the previous class, we were talking about superposition coding inner bounds for a general two-user discrete memoryless broadcast channel. And we saw that using superposition coding, we can achieve the following rate pair. So any rate pair is achievable as long as we can find a joint distribution PXU, where X is, of course, the input alphabet, and U is some auxiliary random variable, such that such that R1 and R2 satisfy these three inequalities involving these various mutual informations. So as long as for a given R1 comma R2, if we can find some PXU such that R1 is less than this, R2 is less than this, and R1 plus R2 is less than this, then we can then this rate pair is achievable. So we can construct encoders and decoders with these particular rates for which the probabilities of error are vanishing in it. Okay, so this is of course an inner bound, which means that it's possible to construct codes if we can find such a joint distribution and the rates satisfy these inequalities. Now, at the face of it, for general broadcast channels, it's possible that R1, R2, which do not satisfy these properties for a given PXU, for any PXU, but could still be achievable. But that turns out to be impossible if the channel is degraded. Okay, for general non-degraded broadcast channels, there are R1, R2 pairs which do not satisfy these for any PXU, but still can be achieved. It is possible to construct encoders and decoders for which the probabilities of error are vanishing in it. But on the other hand, if we have a degraded broadcast channel, a degraded two-user broadcast channel, then this is the best possible you can do. You cannot achieve any rate pair which does not satisfy these inequalities for any px comma u. Okay, and as a quick recap, the main idea was that you consider this clustered codebook, which we call the superposition codebook, wherein code words are all, so you construct cloud centers, so 2 to the nr too many cloud centers, and for each cloud center you consider a cloud codebook, that is a set of satellite code words. So for each cloud center, we have 2 to the nr1 many satellite code words, and while user 2 decodes to sort of the best cloud center, the user 1 can decode not just the cloud center, but also the satellite code word. So the cloud centers encode the messages for user 2, whereas the satellite code words in each cloud encode the messages for user 1. Okay, and here implicitly the random variable u indicates a distribution or represents a distribution on the cloud centers, whereas px given u is sort of the distribution of the satellite code words given the cloud center. Okay, but note what are transmitted are actually satellite code words. Okay, and earlier we've seen that for the binary symmetric broadcast channel, the achievable rate region looks something like this. So it is the region enclosed by the x-axis or the R1 axis, the R2 axis, and this red curve. Okay, and for but if we did plain old TDMA, then only the line joining these 2 points, that is the triangle enclosed by the R1 axis, R2 axis, and this blue line can be achieved. So superposition codes can do better than TDMA. So this was for the binary symmetric broadcast channel. In the previous class, we also looked at a more general binary input, binary output broadcast channel. We did some numerical evaluations, and for one particular example broadcast channel, so this was degraded. So for this degraded broadcast channel, we saw that superposition codes can actually let you achieve the region enclosed by these black lines, whereas TDMA can only get you the region enclosed by the red line and the R1 and R2 axis. So it's this triangular region which is achievable using TDMA, whereas superposition codes can do something more. Okay, and so this is what is achievable. So we can design superposition codes which get to these rates. And today we'll see that for degraded broadcast channels, this superposition codes are the best that you can hope for. So you cannot achieve any rates outside the black region if the channel is degraded. All right. So we'll see a converse proof specialized for degraded broadcast channels. And then we look at the special case of the binary symmetric broadcast channel. And in fact, I'll show that this particular rate. So go up. Right. So this set of rates are in fact the set of all rates satisfying these inequalities describes the complete capacity region for the binary symmetric broadcast channel. Okay. So before we proceed, are there any questions regarding the achievability proofs? All right. So so far we've seen a couple of converse proofs. First, we did the converse proof for the point-to-point discrete memoryless channel, and then we also did the converse proof for the two-user multiple access channel, discrete memoryless multiple access channel. And if you recall, there were only a couple of tricks or a couple of tools that we used. One, of course, is Fanos inequality. That is sort of the most important tool when you want to prove any converse result. The second was to identify a suitable Markov chain and apply the data processing inequality. Right. So these were sort of the two major tools. The other tool was that whenever we have sort of an n-letter mutual information, we try to write it as a sum of single-letter mutual informations using the property that the channel was memoryless. So broadly speaking, in any channel coding problem, these are, for many channel coding problems, these are three main steps: Fanos inequality, data processing inequality, and the third is the memoryless property of the channel. All right. But for the multiple access channel, there was one little extra step, and that was identifying a suitable auxiliary random variable. And that is going to become even more important when we do the converse proof of the broadcast channel. All right. So yeah. So what we'll show now is that for the two-user degraded memoryless broadcast channel, the capacity region is given by this set of rate pairs. So R1 is less than or equal to the mutual information between X and Y1 given U, and R2 is less than or equal to the mutual information between U and Y2. And this has to hold for some joint distribution Pxu, where the size of the auxiliary random variable is equal to the minimum of the size of X, size of Y1, size of Y2 plus 1. So for example, if all the input and output alphabets are binary, then the auxiliary random variable must be ternary. Okay. So this turns out to be the capacity region for the two-user degraded broadcast channel. This is in fact the same as what we saw for so this is the same set of rates which is achievable using the superposition coding inner bound, but except for a slight difference which may seem like a difference, and that is we don't have a third inequality involving the sum rate. All right, which seems a little surprising. So what happened to the sum rate? And here what we'll see is that the sum rate is automatically taken care of in these two inequalities itself. And that is because we're specializing ourselves, we're restricting ourselves to the degraded broadcast channel. Okay, so what happens in a degraded broadcast channel, which is different from other channels? For a degraded broadcast channel, we have the following Markov chain holding true. So we always assume that y2 is degraded with respect to y1, that is user 2 is degraded with respect to user 1. If not, you just interchange the roles of y1 and y2. So and r1 and r2. Right? So since user 2 is degraded with respect to user 1, we have the following Markov chain being true. Okay, so x, y1, y2 forms a Markov chain. And if you bring in the auxiliary random variable as well, then this is the Markov chain that holds for the joint distribution pu x y1 y2. Okay, and but for general broadcast channels, non-degraded broadcast channels, we don't have this Markov chain holding true. So y1, y2 need not be conditionally independent of these two given y1. So for general broadcast channels, we only have that u x y1 comma y2 forms a Markov chain, and this set of rates does not completely define the capacity region. There are rates outside this region which are actually achievable. So this is true only if this condition holds, but in general this is not the capacity region. So for the converse, we will prove it assuming that this is the actual joint distribution of px, y1 and y2. Okay, so let's see what happens for the sum rate. So why don't we have an inequality for the sum rate for the case of the degraded broadcast channel? So recall that for the superposition coding in a bond, we also had this extra inequality, that is r1 plus r2 is less than or equal to I x y1. Okay, but we see that this is not this is missing here. So it turns out that if r1 and r2 satisfy these two inequalities, then this inequality is also satisfied. So let me call this inequality 1, let me call this inequality 2, and let me call this inequality 3. So for degraded broadcast channels, if equation 1 and equation 2 are satisfied, then it automatically implies that equation 3 is also satisfied. So let's see why that is the case. So what we have, we know that we'll start with r1 plus r2. We want to show that r1 plus r2 is less than or equal to the mutual information between x and y1. Okay, and under the assumption that we have this particular Markov chain. So r1 plus r2, if we use the inequalities 1 and 2, we know that r1 is less than or equal to the mutual information between x and y1 given u plus the mutual information between u and y2. Okay, so r2 is less than or equal to iu y2, and r1 is less than or equal to ix y1 given u. Okay, that's good. So ultimately we want to show that this quantity is less than or equal to the mutual information between x and y1. Okay, so let's start by working with this second term over here. I have x, y1 and y2 on the right hand side, but ultimately what I want are just x and y1. So let's try to eliminate these variables one at a time. Okay, so we have x, y1, u and y2. So we need to somehow eliminate u and y2 from this expression. Okay, and we can only use upper bounds on all of these. So let's first try to eliminate y2. So let's keep the first term as it is. I claim that the mutual information between U and Y2 is less than or equal to the mutual information between U and Y1. Can someone tell me why this is true?
So data processing quality hold.
Exactly. Very good. So here we know that U, X, Y1, Y2 forms a Markov chain, and in particular U, Y1, Y2 forms a Markov chain. U, Y1, Y2 forms a Markov chain. So just by using the data processing inequality, the mutual information between U and Y2 is going to be less than or equal to the mutual information between U and Y1. Here we just use data processing. Okay, so we have this to be less than or equal to I, U, Y1. Okay, so this, let's see what we can do with this. So I have I, X, Y1 given U plus I, U, Y1. Correct? So can I write this as I, X, U, Y1? Why is this true?
Sir, if you will expand it with chain rule, then we'll go to previous
Exactly.
section.
So this is just the chain rule, right? So chain rule says that the mutual information between X, U, and Y1 is equal to the mutual information between U and Y1 plus the mutual information between X and Y1 given U. Okay. So this comes from chain rule. Okay, that's good. Okay, so now I have I, X, U, Y1, but ultimately what I want is just X, Y1. Correct. So let's try to write down this mutual information in terms of entropies. So I have H of Y1 minus H of Y1 given X, U. Now, is it possible to eliminate uh, U from this expression? So what can you say about U, X, and Y1?
Sir, y1 depends only on x, whatever we are getting.
Correct. So Y1 is conditionally independent of
Independent from
U
yes,
given X.
yes.
Right. So since U, X, and Y1 form a Markov chain, so given X and U, Y1 it depends on X alone. Right. It's independent of U given X. So this is just H of Y1 minus H of Y1 given X. And that is because U, X, Y1 forms a Markov chain. So this is just I, X, Y1, which is exactly what we wanted. So clearly, if conditions 1 and 2 are satisfied uh, for the degraded broadcast channel, if this Markov chain holds, then condition 3 is also satisfied. Okay, so this rate region over here, which is described over here, is the same as the rate region for the rate region achievable using superposition codes for the degraded broadcast channel. Okay, So that's good. So now we know that the two rate regions are equivalent. The question is now, how do you show that this any point outside this region is not achievable, or put slightly differently, any R1 R2 which is achievable must satisfy this for some for some pxu. Okay. But we'll show it in a slightly relaxed fashion. So we won't make any assumptions on the alphabet size of the auxiliary random variable. We'll first prove it for a very large alphabet, and then it turns out that there are other techniques, one which is called the convex cover method, which lets you reduce the alphabet size of the auxiliary random variable from something which is arbitrarily large but finite to something much smaller. Okay, and we won't really concern ourselves with the details of how we go from a large alphabet size to a small alphabet size. But right now we'll just assume that we will show that as long as R1 is less than this mutual information, R2 is less than or equal to this mutual information for some pxu, where you can be as large as you want, it's good enough. Okay, so the tools that we'll use to prove to prove this converse result, to prove the outer bound, are the following. So first, it's always Fanos inequality. That's sort of the basic thing that you use. So if we use Fanos, how will we use Fanos inequality? So we'll use it in the following fashion. So we know that given y1, you should be able to recover m1, the first message, with arbitrarily low probability of error. And from y2, you should be able to decode the second message with arbitrarily low probability of error. Okay, so in any problem, whenever you're trying to prove a converse result, the way you apply Fanos inequality is to identify what is to be decoded and from what it is to be decoded. Right here, m1 is to be decoded from y1n, and m2 is to be decoded from y2n. Okay, so just by applying Fanos inequality on these two, this is the problem. So this is upper bounded by the binary entropy of the probability of error for user 1 plus the probability of error times log of the size of the alphabet for the first message, which is 2 to the L1. And similarly for user 2, this quantity, this conditional entropy, is upper bounded by the binary entropy of the probability of error for user 2 plus the probability of error for user 2 times log of the size of the second message, which is 2 to the L2. Right? But the probability of error of user 1 and the probability of error of user 2 are both upper bounded by the probability of joint decoding error, that is the probability of either of them going wrong. So I can just say that PE is the probability that M1 hat is not equal to M1 or M2 hat is not equal to M2. Right? So either of them going wrong. And the probability that one of them, say user 1, goes wrong is upper bounded by the probability of either of them going wrong. Right? And we know that so log of 2 to the L1 is equal to just L1, which is n times R1, and log of 2 to the L2 is L2, which is just n times R2. Okay, so we'll use Fanos inequality. We'll use these inequalities in later on. Okay, so that is one key step. Another key step is to identify the right auxiliary random variable. Okay, and that is crucial in deriving this outer bound. Okay, and the right what we want. So you can't be anything arbitrary. So in particular, we'll choose the following. We'll choose the auxiliary random variables in a particular fashion. Okay, so we'll choose U such that, in fact, a UI for each I, such that UI xi y1 of I, let me call it x of I, y1 of I, y2 of I form a Markov chain. Okay, because this is really what has to be satisfied. Right, so we want to identify a suitable auxiliary random variable. It doesn't matter how you choose this UI. It doesn't matter how large the alphabet size is for UI. As long as this Markov chain is satisfied, and you can prove that the R1 and R2 must satisfy those those two mutual information inequalities, we are done. Okay. So this is so these are the random variables that we're interested in, and these are the inequalities that need to be satisfied. Okay, these are the Markov chain conditions that need to be satisfied. Okay, so we'll make one more sort of reduction, and in particular, we'll assume that the channel is a physically degraded broadcast channel. So note that if we want to prove an upper bound, if you want to prove an outer bound, it doesn't matter for which degraded broadcast channel you prove. So the capacity region, we proved in an earlier class that the capacity region for P y1, y2 given x. So take any general two-user broadcast channel. So this depends only on Py1 given x and Py2 given x. All right. So as long as you have, if you have two channels for which Py1 given x is equal to Py2 given x, but Py1, y2 given x are different, it doesn't matter. The capacity region will still be the same. So if I have a P tilde y1, y2 given x and a P y1, y2 given x such that P tilde of y1 given x is equal to Py1 given x and P tilde y2 given x is equal to Py2 given x, then it means that both have the same capacity region. Okay, and so what we will do is we will prove the outer bound for we will prove this for physically degraded broadcast channels. Broadcast channel. So this implies that this Markov chain holds, and therefore by extension this also gives us the capacity region for stochastically degraded broadcast channels. Okay, so these are the tools that we will use. So first it's to use the Fanos inequality on the correct random variables, and then identifying the auxiliary random variable suitably, and we'll identify that in a bit. But so far, are there any questions? Okay, so let's start with where we always start. So you start with NR1. So we want to prove upper bounds on R1 and R2. Okay, so we start with NR1, which is basically the entropy of the first message, M1 to the L1. Right. So we start with an entropy, and we want to somehow express this in terms of some mutual information. Right? So we'll write h of M1 L1 as the mutual information between M1 L1 and the Y1 N, because we ultimately want this term. And the remaining term is h of M1 given Y1 N. Right? That's again by definition of the mutual information. The I M1 Y1 is equal to h of M1 minus h of M1 given Y1. So this is what we have. Okay, and now you can immediately use Fano's inequality over here. Right, we use Fano's inequality to show that this term must be small. So if we have any scheme, it doesn't matter how we are constructing the code, as long as you construct any code for which the probability of error is vanishing in n, this condition must always be satisfied. Right? So this conditional entropy must be tiny. Okay, so then we have NR1 to be less than or equal to the mutual information between M1 L1 and Y1 N plus some small quantity, right? Some n times epsilon. Similarly, for the second user, we have the same thing. So NR2 must be less than or equal to I M2 L2 Y2 N plus n times some epsilon. This is at most n times some small epsilon. Okay. Now earlier, if you recall what we did for the multiple access channel and for the two user, sorry, the single user point-to-point channel, we immediately express this in terms of xn yn, and then just by using the data processing inequality, and then we showed that since the channel is memoryless, it is less than or equal to n times the mutual information between x and y. Okay, but that's not good enough. So for the broadcast channel, if we immediately bring in xn from m, we replace m with xn. It's a valid inequality, but that doesn't give you the best outer bound. It gives you something which is much more loose, and then there'll be a gap between the inner bound and the outer bound. So the trick is to identify the correct auxiliary random variables so that we get a much tighter outer bound. And for this, again, so identifying the right auxiliary random variable is really an art. Right? You try with different choices of the auxiliary random variable, and you choose the one which gives you the best rates. In this case, we choose the auxiliary random variable so that it somehow the rates that you get, the outer bound that you get, matches with the superposition coding inner bound. And in many cases, that is not easy. It takes a lot of effort in identifying the correct auxiliaries. And this really is the hardest step in proving the converse result for general broadcast channels, identifying the correct auxiliary random variables. So in this case, we have some hints. If you look at this, if you think about what we did for the superposition coding inner bound, the random variable u was identified with the message for user 2, right? It corresponded to the cloud centers. But if we choose just u to be equal to m2, then it doesn't give you the best outer bound. it turns out that the best u that you can choose is ui tilde equal to m2 and y1 raised to I minus 1. Okay. Now this choice is not evident. It's not obvious at all. So if someone tells you, then you can prove this. But coming up with this is not easy. Okay. So if we choose ui tilde, we'll slowly see why this is ui tilde and not just ui. But this will be sort of an intermediate auxiliary random variable, and this is equal to m2 and y1 to the I minus 1. So y1, y2 up to yi minus 1. Okay. And so let's think about how things behave. Right? So let's look at the dependence of various random variables. Okay. So first we have three things. We have m1, m2, and xn. Correct. So let's keep this. Right, so we have m1, m2, and we have xn. Right, we'll look at x of 1, x of 2, up to x of n. Okay, and so this is sort of the dependence. So conditioned on each of these xi's, so y1 of 1, given x of 1, y1 of 1 is independent of the messages, and it is also independent of x of 2, x of 3, x of n, and so on. y1 of 2 up to y1 of n. Since the channel from xn to y1n is a memoryless channel, so given x of 1, y1 of 1 is independent of x of 2, it's independent of y1 of 2, and so on. It's independent of all of these. Okay, and note that the channel from y1n to y2n is also memoryless. So y2 of 1, y2 of 2, and so on, up to y2 of n. Right. So the map from these messages to the corresponding xn's are all sort of independent of each other. Right. So given y2, so given this quantity y2 of 1, given y1 of 1, y2 of 1 is independent of everything over here. So it's independent of all of these quantities, all of these random variables, given y1 of 1. Right, so similarly, y2 of 2, so conditioned on y1 of 2, y2 of 2 is independent of everything else. It's independent of all of these random variables because the channel from y1 to y2 is memoryless. Right, so similarly, this holds for each of the y2 of i's. So given y1 of I, y2 of I is independent of all of these other random variables. Okay, and similarly, if you look at the y1 of I, so given x of I, y1 of I is independent of all of these terms. It's independent of all of these. So given this, this is independent of all of these. Given this is independent of all of these in the blue region, light blue. Okay, and these are crucial points that we will use in the proof. Okay, so given y1 of I, y2 of I is conditionally independent of m1, of m2, of xn, and also of y1 of I minus 1, y2, I minus 1, all the other yj's and y1j's and y2j's. And similarly, given x of I, the random variable y1 of I is conditionally independent of the messages m1, m2, the x I minus 1, and y1 I minus 1, y2 I minus 1, and so on. Okay, and all of these just follow from the fact that the channels are memoryless. Okay, and that is something that we will use. All right, so this implies, so since given x of I, y1 of I is independent of all of these, we have ui tilde x of I, y1 of I forming a Markov chain as we need. Okay, so let's start with the mutual information. So we know that n times r1 is less than or equal to this quantity plus n times some small quantity epsilon, which depends on the probability of error. Okay, so this epsilon tends to 0 as the probability of error tends to 0. Okay, so let's bound this particular quantity, the mutual information between the first message and what is received by the first receiver. Okay, so first we'll see that this mutual information is less than or equal to I of m1 y1 y1n given m2 l2. Okay, and the reason why that is true is it's you can get this by expanding the mutual information in expanding a certain mutual information in two different ways. So this is im1 l1 and y1n given m2 l2. Okay, so maybe I can, there are of course different ways to do this. Maybe an easier way to do it is just by writing this this quantity in terms of entropies. So we have I of m1 l1 and y1n, which is h of m1 l1 minus h of m1 l1 given y1n. Now, h of the first message, the entropy of the first message, I claim is the same as the entropy of m1 l1 given m2 l2. Why is that true? So this quantity is the same as this quantity. So anyone, why is the entropy of M1, the first message, equal to the entropy of the first message given the second message? So what are we assuming about the two messages? What is the dependence between the two messages? Yes, anyone? What is the dependence between the two messages? Are they dependent on each other?
Yes, sir. They are independent to each other. No?
Exactly. So they're independent of each other. So
Yes, sir.
M1, the message for user 1, is independent of the message for user 2. So H of M1 is equal to the H of M1 given M2.
Okay, so only first term can be written like this, no, sir.
Correct. Only the
Okay.
first term. Only the
Okay.
first
Oh,
term.
then it is
We
we
still
can
have
write
one
it.
more term
Yes.
to take care
Oh,
of. So
okay. Okay.
this is equal to
Actually,
this.
I was confused. Totally, you have written entire
No,
things.
no. Only the first term.
Okay, sir.
So ultimately we want an upper bound.
Okay, sir.
And so now I need to look at the second term. It's only the first message. So the second term is H of M1 given Y1, and I say that this is less than or equal to minus H of M1 L1 given Y1 N M2 L2. Why is this true?
Again with previous argument.
No, so in this case, conditioned on Y1, M1 and M2 may not be independent of each other. So this is a strict equality. So this term is equal to this term, but this term may not be equal to this term.
Okay, sir.
Right? And the reason why you can do this is simply because conditioning reduces entropy. Right? So if I condition on another random variable, then this quantity reduces to this. So this entropy is less than or equal to this entropy, but we have a negative sign. So the negative of this entropy is less than or equal to the negative of this. Right? And this quantity is essentially this mutual information that we have over here. Okay. So is that clear? Are there any questions? So we split the mutual information in two terms, two entropy terms. The first entropy term, we introduced the second message M2 just because M1 and M2 are independent of each other. For the second term, we know that conditioning reduces entropy. So if the entropy can be smaller, then it means that the negative of the entropy can only be larger. Right? And that is how we get this first inequality. Okay, so now we have this. Let's try to just split this mutual information using the chain rule. So just by the chain rule, we can write this mutual information as a summation I going from 1 through n of the mutual information between m1 and y1 of I given m2 and y1, y2, y3 up to, so y1 of 1 up to y1 of I minus 1. Okay, so here this is just chain rule. Okay, but now we said that ui tilde is equal to this quantity. So this is just, I'm doing nothing here, but just by renaming the random variables. So sorry, this should be ui tilde. Okay. So this is ui tilde. So now I have this, right? But ultimately I want everything in terms of the mutual informations between the x and the y given u. Okay. Okay. So let's see what we can do. Now I have this particular mutual information I m1 l1 and y1 of I given ui. Okay, and I claim that this is less than or equal to, so this each of these mutual information terms is less than or equal to this mutual information term wherein I have m1 l1 and x of I. Okay, and the intuition is that the intuition over here is basically that how much information does, so what does this term represent? It represents how much information m1 gives sorry, how much information you get about y1 given m1 and ui, right, ui tilde. So if I give you another random variable, then the amount of information that you get is obviously more. So x of I and m1 l1 obviously give you more information about y1 of I conditioned on ui tilde than just m1 alone. Right, so that's of course intuition, but of course we also need a proof, and the basic idea is just this. So this is equal to this mutual information y1 of I given ui tilde plus another mutual information term, right, and that is I of m1 sorry x of I and y1 of I given m1 l1 and ui tilde. Right, I've just introduced a new term over here. So this quantity is less than or equal to the same quantity plus a new mutual information term. Mutual information is always non-negative, and just by the chain rule, if I combine these two, I get this particular mutual information term. Okay, but now we'll now again invoke the Markov chain inequality. So we know that given x of I, y1 of I is independent of m1 and everything else. Right. So this is equal to the summation I going from 1 through n of h of y1 of I given ui tilde plus, sorry, minus h of y1 of I given x of I m1 l1 and ui tilde. Right. So, but given x of I, we know that y1 of I is independent of m1. Right. So this is basically the same term minus the first term minus h of y1 of I given x of I and ui tilde. And this is just this mutual information over here. Okay, so this is by the Markov chain. All right, so we get this particular mutual information term. Okay, now I can write this as 1 over n times summation I going from 1 through n of 1 over n times the mutual information between x of I, y1 of I given ui tilde. Okay, and this whole term over here, I will write this as I of x y1 given u bar, where u bar I will write as some random variable. Let me call it W, and U tilde, where W can take values 1, 2, 3 up to n. PW is basically uniform on 1, 2, 3 up to n, and conditioned on W equal to I, PU bar, given that W equal to I, is basically PUI tilde. If I take it to be this form, then this quantity just evaluates to this conditional mutual information I, X, Y1, U bar. So this is in fact quite a huge auxiliary random variable. So U bar is equal to, is actually a triplet. It consists of W, it consists of M2, L2, as well as Y I minus 1. All right, but nevertheless, we've shown that this mutual information is less than or equal to n times this mutual information, n times some I, X, Y1, given some auxiliary random variable which satisfies U bar, X, Y1, Y2 is a Markov chain. Okay, so this is satisfied. Okay, so this is so now we got a bound on nr1. So nr1, n times r1 is, we know that if the probability of error is vanishing in n, then this is less than or equal to n times I of X, Y1 given U bar plus n times some epsilon, which depends on the probability of error. So as the probability of error is vanishing, this epsilon is also vanishing in n. So we got the first inequality, and now we just need to get the second inequality. Right? And the second set of inequalities also is done in a very similar fashion. So maybe we'll go through that in the next class. All right, but the ideas are basically the same. Right? So there are three key points. One is to know when to use Fanos inequality. The second is how do you identify the auxiliary random variable, and the third is what properties of, like, what Markov chains do you have in the set of random variables, right? And the set of Markov chains, the dependence between random variables can be represented in terms of this figure over here, right? So you have, so this is sort of a graph, right? It's a graph which represents the Markov structure among all possible random variables that we have. And in particular, if you take any random variable over here, let's say this one or this one, and you look at the chain coming from beyond outside this. So if you just pull this out, then conditioned on this. So if you cut one of these nodes over here, so if you remove X of I, you know that Y1 of I, this breaks the chain between Y1 of I and the rest of the random variables, right? And that means that this conditioned on X of I, Y1 of I is independent of all of these. So this graph has the nice property that if you remove some element of this chain, then conditioned on this, on the element that you have removed, the two pieces are independent of each other, are conditionally independent of each other. Okay, and identifying these chains is important in information theory, but similar ideas are also used when you talk about problems in machine learning, where you represent various random variables using these Markov random fields or probabilistic graphical models. So in some sense, what we've drawn over here is a probabilistic graphical model. It is sort of a graphical model which represents the dependencies among various random variables over here, and identifying and just seeing what this the structure of this graphical model is helps us identify the right kind of information inequalities that we have to use in order to derive these outer bounds. Okay, so in particular, this if you sort of write it in a particular fashion, this is just a tree, right, where M1, M2 form the roots of the tree, and all of these y of i's form the leaves of the tree. So if you just rotate it by 90 degrees, then it will have this tree structure, and because of this, you also infer the conditional independence among various random variables. Okay, so we'll stop at this point and continue with the rest of the proof in the next class. But are there any questions here? So the proof is fairly involved. So you should go through it once again. Try to see each step of the proof. So the first step, to start with, you should look at each step, and without looking at these blue comments over here, try to identify how you get each step. So try to go from this step to this step, this step to this step, and so on. Try to understand how each step follows from the previous step, what tools are used, what inequalities are used, what properties of random variables are used. And once you get each step, you'll also gradually understand the high-level ideas that are used. And as I mentioned, there are only 2 or 3 high-level ideas that are used: Farnham's inequality, and then identifying the auxiliary, and identifying the right Markov chains. And then you'll see how all pieces fit together like a nice jigsaw puzzle. Okay. All right, so let's stop at this point. We'll continue in the next class.
Okay, thank you.
Thank you.
Thank you, sir.